Okay, thank you very much for attending this session. It would be like a very, like a different kind of session, this one, because it's actually pretty broad, and it will talk about how to handle software updates, focusing on Linux devices, and in the way that Android does updates. So one of the things that actually never was like simple and on Linux devices was how do we have a strategy for updating those devices, because there are many ways to accomplish that, but the way Android actually does is pretty sweet. So the title of this presentation should be how can we achieve Android-like update software updates on Linux embedded. But again, we are leveraging a couple of open source technologies. The first one is a software update by SFO17-415, that is the maintainer of U-Boot. And then Eclipse Hawkbit, that goes under the umbrella of the Eclipse IoT new projects. And we just combine those things together in order for having like a pretty much sweet way to handle Android updates. So I want to like thank you, my team, and some testers, in particular Eric Nelson and Gary Bisson from Boundary Devices, and also our friend from Linaro, Amit, that allowed us to be here presenting this thing. So the agenda for this session is talk about a little bit about motivations, why we want to do that. We would be talking about how Android actually does updates. We will be introducing software update as an update agent for Linux. Then we will be talking how can we remotely handle rollouts. And then we will be talking about the fusion of these two technologies in what we call Update Factory. So the first thing is there are plenty of products out there that may take care of updates on embedded systems, but we are focusing on medium scale type of updates. When we work with customers, not every customer has a billion of devices. Some specialized devices like medical devices are probably 3,000, 4,000, and those kind of customers want like a very general way to handle their updates that is easy to integrate in their existing operating system, and that is reliable in a way they can trust it. So we will discussing about different ways to strategies to approach the problem. Another motivation is, can we do that for both Android and Linux? Okay, so if we have the same two systems that actually make updates in the same way, can we actually have like a platform to handle both? Then obviously we want to track updates, and we want to also customize some metadata that are like handled by the device, and we want to show in the cloud. So basically, we have two basic approaches when we want to do software updates. The first one is the double copy. Double copy is like when we carry two different copies of the operating system, including the kernel, the device tree, and the root file system, right? And and we need the bootloader actually to decide which copy he wants to boot. The single copy features like what we call an upgrading software. So we have something that is in charge to copy a file or transfer an image on a partition or multiple partitions. And you can share the kernel, or you may want to update the kernel if your update system single copy is segregated, so it's like separated from the main operating system, and we'll see some examples. And again, the bootloader should be in charge to boot the device in upgrade mode. So this is like a typical scenario of a dual boot partition when we have a double partition for managing the boot, right? So This is not the unique way to handle that, but let's say that in any embedded system we have a boot partition, a root file system partition, right? In this case, we have two different bootable systems. So we have two boot partitions where we have the boot script. Boot script is just like the uboot.scr file, right? It's the scripting thing that you can do for like injecting commands and variables from uboot. Then we have the device tree, we have the kernel, we have a RAM disk, and then we have also the root file system. So we are carrying, using like a boot environment variable, a selection, and we decide which system should boot. We may have also a single boot partition, double copy. So we are sharing the boot partition, and the boot script actually decides which root file system should be booted. This is the single copy scenario. It's very simple here, right? So we start having one boot partition. The system recovery can be like thought in two different ways. The first one may be like a RAM disk that is in the boot partition with its own kernel, not. It's like totally free, depends on who implements it. Or we may have a system recovery that's just a binary blob in the, just like stored in a non-partitioned space after the bootloader. So it really depends. We will see a couple of examples where the second one is also implemented. And then usually we have like a root file system on a different partition. So what are the pros and cons? The double copy is actually, he has a fallback. So if something goes bad, you have still one operating system that is always bootable. And it's pretty easy to implement. However, it's very cost expensive in terms of storage, right? So if you have like a lot of, you have a big like root file system, you're gonna double it. And if you have multiple partition, right, you have to reproduce the same partition twice. So, you gotta think about it. So you require a mechanism to handle that. And obviously, you gotta know which of the two systems is actually running because they are the same. Single copy is like sweet because it requires a smaller amount of space. Usually the updating mode lives in RAM. You can overwrite the entire partition, right? So you can overwrite everything because it's running in RAM. Usually it's used for factory resets, so you plug a USB key and you have a RAM disk that starts there, and you can pretty much do what you want in your eMMC. Some cons are you don't have a real fallback. However, right, what you can do is to have the updating process to start again, right, and try to be completed. So if something goes bad, I don't know, like you have like a power interruption, the system just reboot in the update mode and try to write again. In the simple scenario I showed you before, right, we are like sharing the kernel. So, you cannot update the kernel, or if you can, and you have like some problems, you don't have any more like a kernel to boot the RAM disk where the software update mechanism was running. Okay, so remember that what we want to accomplish is to have like a unified strategy between Android and Linux. So what Android updates looks like? So what we do is the preparation that actually happens on the regular operating system. Then we execute the upgrade in a purpose-built recovery OS. And then, the preparation on the device, you have an Android phone, so you know perfectly how it works. You register on the cloud, you have polls for available updates, you have notification, you download it, you want to apply the update, and then you reboot in recovery OS, right? And the entire execution of the update is handled by the recovery binary. So I want to just give you some hints, and I'm taking the IMX6 family of microprocessors, right? So the bootloader, right, it can read like a register that is called reset cause, and he knows that you want to like reboot the system in recovery mode. So he boots the recovery system. So the recovery is the name of the binary actually that Android uses for handling the recovery. So recovery starts, recovery unpacks the update file, because as you know, right, Android updates are just signed zip archive with a particular structure, where inside you have an updated script written in some scripting language called 85, and the update binary executes actions in that script, writes log, write the operating system, the new image on, you can write row write, for example, the system image, or whatever other data in other partition from the script, and then you reboot on the regular OS. This is like just to show you what happened in the boot script, right? So if you have a boot script, this is exactly what happens when we want to read the register, and then we trigger the update OS loading. Okay, so what are the advantages of Android? So it's a single copy, right? I don't know what is a little bit weird, this one. Okay, so let me see. All right. So it's a single copy. The OTA agent runs in the regular OS, so you don't need to interrupt operation, you have network access, you interact with the user, you have the full API available, right? This is the battery low, you have the Wi-Fi, you have 3G working. So all the artifacts are prefetched already before starting the procedure. So how can we approach the same concept using Android, right? So we start from exploring software updates. So software update is this project written by SFO17-415 from Denks Engineering. It's written in C. It runs as a daemon. He has his own update files based on the CPIO format, right? We don't reinvent the wheel. There are many handlers for different kind of writing. And if you want, you can script your own thing using the Lua language. Also shell script, obviously. So, main feature of software update, right? It supports local storage as a, if you want to load artifacts. So the SWU file. It supports local peripheral devices. So for example, if you want to flash some binary code on an MCU, what you can do is actually stream the update from the application processor to the MCU using the UART or USB communication. If you want, you can use an internal web server, Mongoose, and you can upload your own image, right, on the software update. You have also remote interfaces, so you can gather your image SWU file from an HTTP remote server, FTP, and this is the most sweet part. So software update comes with a module called Suricata, which implements the API of Hawkbit, and we will be talking about that. Also, okay, you don't see really well here, but it obviously supports signature and encryptions of the update file. So this is a schema, right, of the architecture. So we have the installer that is the main core, right? Obviously we have the parser, And the parsers is just using the libconfig. We have a handler manager. So if you want to access, you want to write raw data, we want to access U-Booth environment variable, we want to write on different kind of storage technology. We have a notifier, right? So we can track the state of the process. And again, here we can store artifacts in local storage. We can retrieve from remote file. We have available a web server running into the software update to upload the images manually. We can write custom protocol if you want to stream an update to like another component of the board. And obviously we have a sweet implementation of the Hawkbit API inside software update. As I said, right, the image file format is the CPIO. So we have a CPIO header. We have a descriptor file. This descriptor file is just like a descriptor for the update process. You have variables, data structures like images, right? Scripts. You can do pre-install script, post-install script. You can specify also file. Also the data type file is supported, right? If you wanna, it's not really a good thing to do, but if you want to just overwrite a file in your update, you can do it. The sequence has to be this, so the software descriptor has to be the first, so you gotta be sure that in your in how the CPIO is assembled, the first file is the software descriptor file. So let's see, in the scenarios that we analyzed before, how actually software update gets in. So in the dual boot partition, right, we have just software update as a daemon that runs in the root file system, right? And he handled the overwriting of some U-Boot variables, so you would know which system has to boot. In the single partition, in the double copy single partition case, same thing. We just installed the daemon in the root file system of partition 1 and partition 2, and the mechanism is exactly the same. We are just sharing basically the kernel and the device tree and the and RAM disk. This is optional. If you don't want a RAM disk, you don't have to put the RAM disk. For the single copy scenario, right, you can have software updates on a RAM disk, or you can write software update in a space that is not partitioned at all, right? Here I just put some notes on some utilities that are usually very common on this framework. To, for example, reading and setting variables on U-Booth, right? So these firmware, the firmware utilities. In particular, the variable uState, right, tells to U-Booth if you want like to boot in update mode or not. So 0 no, 1 yes. So obviously, software update has security. So the first thing is the software update description file can be signed, right? And can be signed using the private or public key, asymmetric signature, or using certificates, right? So it means that the update file, description file comes from a trusted source. So the system will produce like a new description update description file that is signed, right? And when the daemon is launched, you have to provide a public key to actually run the update, or software update will complain about it. You cannot read here, but I can tell you. So software description contains hashes. So if you want to be sure that what you are installing is what actually has been distributed. The system can check hashes for you. And also, no, that's it for this line. So hashes for just specifying if the image is consistent. Typical example, really quick, right? So software updates comes with some scripts that helps you to generate the CPIO file. Really sweet. So you can just customize this script, and you can decide if you want to sign it with a certificate, you want to sign with just like the private key. And here, you iterate just to create the CPIO SWU update format with the right sequence. Here, I wanted just to show you. So here you have the data structures images. This is a piece of the software descriptor file, right? So we have like some variables. So the data types images contain some variables. It specify where, the type of image, the sum for consistency here, and obviously if there is a mandatory an install script, right? That is executed by software update. Just for give you some like practical coding example, right, about all these properties. Software update supports also encrypted images, right? So if you want to have encrypted images, you can actually encrypt that. You just specify in your images data structures when you are like addressing the particular file name. This is one image, right, that you include in your CPIO. You just like specify encrypted through. Actually, you have created, this is like an encrypted file, right? I'm not like telling you all the path, you know exactly how it works, so just for let you know that you can encrypt images with the symmetric procedure. So, as a part of the Warp X community, we actually use software update for handling firmware updates of the community board. And we are using the single image approach with software update into unknown partition space, right? So it was like one of the two scenarios of the single image that we saw before. Basically, we just boot the system and we flash from the bootloader special image, right? We do that using the UMS, so looking at the eMMC as a map storage, so we copy that, and then we just started, by reading the address or where we loaded the update image. And then we boot the recovery image, the kernel of the recovery image support the USB gadgets, so we have access to the network, and so we can use a USB cable to access the web server with our web browser and upload just an image file that will be flashed on the eMMC as a new software update. But still, this is a kind of thing that, it's not really for production, right? It's something that is pretty interesting and fun, but it's not where we want to go exactly for a large scale implementation. Before moving to that stage, right? We take a look really quickly to Hawkbit. So Hawkbit is this framework and platform, part of the Eclipse IoT umbrella, and the definition is simply to create a domain-independent backend solution for rolling out software updates to edge devices. Very quick. So basically, it comes with a user interface. It comes with a management API, right? So if you don't want to use the user interface, you can have access to pretty much everything using the API. It's written in Java. Works on top of a framework. It's more than a framework, actually. It's called Spring. I don't want to bother you with those kind of things right here. I want to just be more embedded oriented, but So this is like a very well done project. He can support different device management strategies. The first one is direct device integration API, and use HTTP and JSON as a protocol to communicate with devices, or also it may support device management federation API, where you're using actually MQTT or like actually IMQP, right, as a broker for managing your update file. So really quick, right, the architecture. So in purple, you see just the abstraction. So you have the UI, you have the API, you have the DDI API, HTTP, as I said. This is the Device Management Federation API, supporting like IMQP. The thing is, the two repositories for handling artifacts are separated from the application metadata. These ones in Mongo, we actually tested on S3 of Amazon. It works pretty well. MariaDB, MySQL is where application stores metadata. If someone, look at this and say, hey, but this is the only thing that actually doesn't scale, because everything here actually scale, right? So if you want to build a cluster, right, actually Hawkbit is pretty ready. Application metadata is the only bottleneck here, but there are really few data. It's not really massive. So right now you can live, with this kind of architecture without complaining. Okay, so how Hawkbit operates, like how we do like a rollout campaign. So we prepare an update file, right, the SWU file. We create a software module and add the update file to the software module. So it's just like a container. We create a distribution. A distribution is just a container of software modules, and we roll out the distribution to targets. Targets can feature tags, for grouping devices. I can show you if you have time. We have attributes like hardware revisions or custom attributes that we want to double check when the when the device actually communicates with the cloud. So it's pretty like flexible, right? We have logs, we have the operating system that is installed, so it's very verbose, to tell you what exactly is running on the device. Just little quick. So this is my update. I create a software module, just drag the update on the software module, right? I can use the upload feature here, and I upload this artifact, and I just transfer the artifact, drag and drop on the software module. This is the software module. I create a distribution. I just associate this software module with the distribution, and then I just take the distribution and I literally drag the distribution on top of the device. This is a device, right? Just one, for example, and the process starts. You can, also you have suite things on the rollout. You can divide devices per type. So let's say we have Android devices, Linux devices, and we want to run different campaigns, or we have a massive number of devices. We want to test the upload just on 20%, and then if we succeed, we want to cover the other on 80%. So just to say that it's pretty flexible on the use cases that may, we saw our customer pretty happy with this. Okay, so we combine Hawkbit and software update to create Update Factory. So Update Factory in a big word is like platform to manage and deliver software updates, artifacts which are deployed on single copy Linux and Android devices featuring recovery mode. Okay, too much. We manage and deploy Android-like software updates on embedded Linux. How we do this? So we run software update on Linux. So Android comes really 80% ready for it. So we just implement a service that implements the update server API just to download and track using the management API, tracking the upload and download and in the install process. But really much, we are not doing anything on the Android device. On the Linux device, we are using software update. Then we have an update server that is actually featuring Hawkbit, right? Then we have EAN server for user authentication. We have an artifact repository that is S3, and then we have a metadata repository that is MariaDB. Okay, so how we do implement Android-like behavior on embedded Linux? So single copy. So what we have done is to do a recovery partition. So let's create the segregated environment that we need, like Android does, right? Creating a recovery partition. Then we have a recovery RAM disk, and then we have a recovery boot script. And the bootloader obviously decides which operating system is booted. Obviously, we have device-to-cloud communication, and device updating status is tracked on the cloud. So this is how the schema looks like, right? On Linux, we have the bootloader. We have a boot partition with the boot script, device tree, kernel, and RAM disk, right? Classic boot partition. Then we have a recovery partition, so a separate partition. We have boot script, device tree, kernel, and a RAM disk. These RAM disk features, right, like the U-RAM disk recovery, right? Imagine this as the U-RAM disk recovery, like in Android. Software update. So software update may have access to a cache partition, like in Android, right, that has the SWU. Or if you don't want a cache partition, just put in the recovery partition your update file. It's it's better to have a separate partition actually to handle all these repositories, all these artifacts, like actually Android does. Android store the zip file for updates into the cache partition. Then this RAM disk, when the use state variable is set from the root file system, the system reboot in recovery mode, right? Execute the RAM disk here and his own kernel. So you can have different drivers, you can pretty much build your own separate system. And this flashes the new rootfs on the rootfs partition. If something goes wrong, this is a really segregated environment, read-only, and so you just reboot the thing, right? The use state variable is still set to 1, because these will be set to 0 when the root partition will be booted, the new one booted successfully, right? So the state will be upgraded by software update, which is running also in the root file system. Here is just to say, okay, we have the suricata module. We just specify tenant name, the device ID, and the URL of the update server. And this is like the device to cloud part. And this is pretty much it. So when you write this successfully, the use state variable is set to 0, and you have like a consistent system, like a consistent updated system. What happened in Android? Okay, so if you remember, our goal is to set like a unified strategy for both Linux and Android. But Android actually is pretty easy, right? Because you have, so let's talk about the IMX6 again. So you remember the register, the reset cause register that the boot script goes and read, right? And he read it, and he knows, okay, I gotta boot the recovery partition. So these partition, the RAM disk, the URAM disk, recovery URAM disk is executed. He goes and take the the system update zip file, and it performs the installation. Remember that Android has 8 partitions, right? So you have many other partitions. So it's something that I'm not like touching on the system, but basically one of these partitions is the where you write the system image. So your zip archive has the script in 85, scripting language where you tell exactly how to handle images to be written in the different partitions. What happens in the device? Well, we just made like a small service and a small client if you have to change those parameters related to update factory, right? And pretty much the thing is done. So when you have some updates available, they are downloaded, and then the app here, client, the service, see that there is a new update available, has been downloaded, and ask you to the user if you want to apply the update, exactly like Android does for your operating system. So again, we are not targeting phones, we are targeting general embedded system. You can use like your 96 board, you can implement this like pretty easy, and I will tell you how the resources that we make available for doing it. First, just to recap what we accomplished, right? So we wanted to address like a medium-scale general purpose CPU SoC deployment. So not millions, but thousands, right? But in a way that is pretty flexible for engineers to adapt at their platform level. We like the Android OTA approach, and so we wanna implement it on Linux. We would like to be neutral, so the backend platform should like handle both, and we should provide the artifacts, right, like this, right, to handle the Android side, and again, on the Linux side, software update is taking care of it. And we published the Yocto layer for supporting update factory. The layer for software update is already available. So if you're building Yocto from scratch, just including 2 layers, you will be pretty much ready to go. We set up like a remote management platform where the update server is run by Hawkbit, but then we have other, obviously other components. So it's like a bunch of microservices that build the platform. And obviously, we implemented like a free tier for testing, and so some companies are testing it just to see if it makes sense to everyone, right? These actually made sense to us, but it's like our vision about how we want to handle those kind of updates. Okay, some links. So we have some documentation, right? Here we had like the meta layer published. There are blog posts for implementing the software update on the WordPads. It's interesting from a very scenario standpoint, because the way it's done here is pretty much like what we saw in the slide with the software update into in a non-partition space, and it's pretty interesting from a learning standpoint. Here we have Eclipse Hawkbit. We have Babbage GitHub where you can check out software update. And obviously, for reference, all the information about how the update works on Android is pretty much documented on the Android developer portal. Okay, so probably I went really, really fast because I was scared to not make it. I want to just show you. Let's see if I can. So here, let's see if I can. For some reason, it's not really centered. So this is like our staging platform, so the development platform. We have 3 devices connected. 2 are Linux. One is Android. I have created some tags, right, just to group some devices for different type. So this is the Android. This is the Linux, right? Sorry. This is Android, and this is the 2 Linux. Sorry, it's like really tricky. Here we have distributions. So I created those distributions just, so I want to just go here, right? So I have different type of distributions. So I created 2 distributions for demo purposes, so I can go back and forth from OS version 5 and OS version 6 on Linux, and another distribution that has just some update of some apps on an Android device. Again, for demo purposes, tomorrow we will have a demo table. I didn't want to do like a full system update because it will take like probably, I don't know, 3-4 minutes, so it's not really feasible in a short time for a demo. But actually, this is exactly what happens when you do system updates. So I created those software modules. Software modules goes into distributions. So I just drag, like I associate like this one and this one, right, with the it's loading. Let's see if it goes. Okay. So it gives me the description of the software module, and this module is associated with the distribution of the same version. If I want to roll out the thing, I go into the deployment window. Let's say that I wanna, so this device, right? So let's say this Linux device is running the 1.6, right? So let's say that I wanna go back. I wanna update that device using the 1.5. What I do is to just do this. Right, what is this? Okay, so I just drag the distribution on the device, on the target. So the system tells me that I have an action. I want to force, okay, so there are 2 modes, force or soft. Basically, the force reboot the device automatically. It doesn't ask the user to boot the device, or you manually, so you don't boot the device manually. The soft, just download everything, apply what he has to apply on the system, but you have to take care of rebooting the device. So I'm doing the forced. So we are in pure demo mode, guys. I hope that everything will be fine. So what we do, so again, was to save and assign. Okay, so now the system is updating. We have the yellow icon. So what happens now is the device pulls the cloud platform. There are updates available. Download the update, right? Put the update in the recovery partition because in the schema I showed you before, the root file system can have access to the recovery partition. Store, well, if we are storing the update file on the cache partition, on the cache, or if we are handling the recovery, the update file on the recovery partition, just put in the recovery partition. When the download is done, the device is ready to reboot. So the state variable is set, the device is rebooted, bootloader read the use state variable, reboot in update mode. So the update RAM disk on the update partition is started, load the entire update system in RAM, take the image, the SWUpdate from the cache, write in the root file system, and then when it's done, just reboot the device with the new file system installed. Okay? So here, I'm not seeing. So it's still upgrading. Okay, so let me just refresh the page. There we are. So the update is finished. If we go here on the installed, we have 1.5. So what we have done is just to, just to play with it, to install like an old version, right, of the OS. And if you drag again the same version, the system knows that it's already installed. It doesn't allow you to do so. So this is why I got to do the switch type of thing, right? So now I can do the same thing with the OS distribution 1.6. Same thing with Android. If you want to update the Android device, I just select the Android here. Sorry. I don't understand. Let me see this. Let's see the tags. Oh, this is Android. So no tag. Okay. If I want to do the same thing with Android, so I take the distribution I have created with Android, and I just do the same thing. So here. Here, forced and soft, right, is disabled. So for Android, usually on embedded, we do the thing to be automatically rebooted. So we just notify the system that an update is available, and if the user says, yes, I want to go for it, the update does everything automatically, right? So when I do like this, okay, so now did I do this? Probably not. Oh, let me see. Let's reload the page to see if the state is, no. Okay. So, Android app. Okay. I was expecting to see this on a different color, like yellow, like before, right? I apologize if you don't have the entire screen that is visible. And so here, I don't know why there is no like the yellow thing. Anyway, the same procedure applies to the Android stuff. So download, reboot in recovery mode, write, and restart again with a new system, with the new system installed. Let me go back to this. Okay, so it's pretty much everything. If you have questions, we have like, I think, 5 minutes.
You mentioned certificates and you said you have to provide it. How is the certificate management done for this?
Oh, well, you use OpenSSL utilities, right, for like signing. It depends on what you want to do, right? You have two options. You can sign the software description file, so you generate your own. So you generate your own private key, and public key, and then you sign with your private key the software description file. Then you specify to software update to start with the -K option, specifying your public key on the device. And so only the update is executed only if the two keys actually matches, right? So this is the first, it's a classical asymmetric thing. So I can execute that description file only if the private key is signed the right public key.
Right, but can you put the public key ahead? Can you manage it so that you have the security that you install the proper public key?
And that's actually a pretty good question, because the only thing you gotta be sure is that you have the public key. So I don't know, see if I have the same, I have 100 devices, right? Am I using, in your scenario, the same public key, or I'm generating different keys for each device? So I have a certificate or a public key for each one of those, one, or I'm generating one different for each device. What is the case you want to explore?
Well, you usually have one public key, right? So you're the vendor, you want to make sure that only your signed upgrades are making it to the device, so you have to have it there prior to the upgrade.
So when you sign the SW description file with your private key, right, and you load your public key on the device in a place, right, and you start the SWUpdate demo with the -K option, specifying your public key, right? Then everything that the software update description file signed with your private key will be recognized by the system.
Okay, but loading that public key and making sure that nobody tampered with it, that's outside of the upgrade process.
You mean on the device?
Yeah.
On the device, you have to store that public key. You need that public key on the device.
Yes, but how do you guarantee that nobody stored a different public key?
Well, if they do it, right, they will not be able to upload the device anyway, because the software description file, right? So let me go back here, right? So we are talking about this. Right, so this is your update file. The update file has this file inside that is like a text file. This just is a manifest of the update. That file can be signed. If it is signed with my private key, only with my private key, only the public key correspondent to that private key, right, can read that file, that signed file.
Right.
I think what you're saying is that the public key must be immutable. You shouldn't be able to change it.
No, absolutely. Oh yeah, and you have two options. You can have like different public keys for a bunch of devices. I've seen that in my experience. Or only one. It's not really secure to have only one. But if you have 1,000 of devices and you want to have the same sign on every one of those, so the same private signing the file and the same public, to verify the sign, is pretty much what we do.
Okay, the management of this is outside of the upgrade process.
Yes, oh, absolutely. When you generate with OpenSSL utility your keys, you have just two keys, and you just put one key on the device, and you sign with your like laptop or your host the signage. This is just the first level of security. Then you can encrypt actually with a symmetric algorithm the image itself also. So you have another level of security if you want to add it. With this, you are just signing this part. With the second level of security, you can encrypt also this one.
Okay.
If I understood well, the such public key would be inside the RAM disk of the recovery mode. Or did I get it all wrong?
No, absolutely. No, absolutely. It would be in the RAM disk.
So the bootloader may authentify the recovery mode before it puts in recovery mode. So
oh yeah. Yes. Oh yes.
So
Yes. Oh absolutely. Everything is checked before doing the update, the consistency. So software update can say I cannot apply these updates, any complaints, if the sign is not aligned, if the software description file is not like signed in the right way.
And a different question: Do you know of any similar work being done for Zephyr instead of Linux?
Well, Zephyr is for microcontrollers, right?
Yeah.
So, okay, so I don't know how. Okay, so for microcontrollers, actually the update is a little bit different. Usually they don't use, for example, HTTP. They use more federated type of protocols. for handling updates, even because we are talking, I don't know, about millions of about 1 million devices. So I don't know what is the strategy they are doing for handling the update. I remember.
I can talk a little bit. We are using, as kind of one of the demos that we did previously on Connect. We are updating Zephyr-based devices with Hawkbit as well.
Okay.
So.
And is there a similar infrastructure?
But you are using double copy, right, on Zephyr?
We have like the double partition
okay,
as well.
I remember
and a bootloader that can verify the signature of the image and do the swapping of the image and so on and so forth. So like the application would download from the Hawkbit server using, for example, HTTP, and we have the logic already, and we're trying to upstream some of the logic as well into Zephyr. That would just simply write, for example, the application to the second partition, trigger the bootloader, and then the MSU device that can be updated the same way.
Okay.
Like this.
So as you are using only single partition for the upgrade, it means that if upgrade is broken, you are only able to boot in recovery mode.
Correct.
Did you consider using, for example, OS3 like AGL does? To prevent such situation, to be always able to boot maybe to the older version, but always be able to boot the device in normal mode?
Yeah, right now, no, because we were just following the way Android was handling that, right? So the thing is, what is the reason of failure and how much time you have to fix it, that failure? So let's say that I delivered an update and everything is pretty segregated, so separated from the system. What can be wrong? Hardware fault, so that the hardware is not working anymore, or something was broken during the process of updating the device. So pretty much in our use case scenario, but yours is perfectly legit for a more mission critical thing, in our scenario, nobody really bothers to restart the recovery process another time to just finish, to complete it. But yes, we should consider if we want a more reliable, we want to have like a backup stuff too. But you cannot do in a single update mode.
Well, if you would use OS3, for example, I'm not advertising, just any other system to ensure that you are always able to boot in a valid OS, then you may remove a couple of things from the RAM disk and all the logic which is responsible for downloading, etc., to system itself, because you are always able to boot some version of the system.
But this is some version, what is
so
it?
You just try to reboot. If the update fails, you reboot one more time, restart the previous version, and reboot the old system. And then you make all the logic which is responsible for downloading one more image, which now maybe will work.
No, you're not downloading from the RAM disk, it's already downloaded.
Okay, but on the RAM disk, you need to have some. What do you do if the update is broken? You reboot to the RAM disk and try to knock on the
if the update is broken, so I'm releasing like a bad update.
Yeah.
So a bad update that actually keep the thing absolutely unusable. Yeah, you are done. If you write the bad thing, but usually, I don't know. Let's say I did something on the root file system and the boot hangs doing init, or I'm doing something worse. The kernel is not booting at all.
You're not upgrading kernel, I think.
Huh?
You're not upgrading kernel.
I am. Oh yeah. I am. Oh yes. Look, I am in this scenario here, so I am upgrading the kernel. Let's see. Yeah. So because I am in a segregated environment, I can completely override the boot partition. So I'm also upgrading the kernel.
Okay.
Yeah. So going back to your point, if I have a wrong update, well, it should not happen in the real world. But no, I am like stuck.
Well, your recovery mode could get
exactly. So I should, but because the recovery mode has no networking functionalities, because it's like Android. If you remember, there was a slide here where I was telling about the Android, how Android I'm downloading everything in OS mode, so in the real OS. So my RAM disk doesn't have any networking like capabilities. I don't have drivers to deal with networking, Wi-Fi, or whatsoever. This is exactly what Android does. All the artifacts are already downloaded by the user space regular OS. So in that situation, I constantly boot and boot and boot and boot the update system, right? The OS that actually works. But when I flash, I'm just flashing the wrong image, right? I'm flashing the wrong OS update, and the device is like pretty much unrecoverable automatically from that standpoint. So, and you bring a good point. What happens in the real world? How many times are we actually doing something like that? We are like rolling out like something that may like just make the device unusable. So it really happens a few times, but to answer your question, in that case, there is nothing that you can do from.
Okay, but in the real world, the most often is the rootfs upgrade. The kernel upgrade is, let's say, more critical, more risky.
No, well, Android does kernel upgrades.
Yeah, I know. But the guys from the AGL are using this only for the rootfs upgrade, because usually you would like to ship a new UI or anything
Correct.
like this.
You're in this scenario.
Yeah,
right.
Exactly. So that's why they use the OS tree, to ensure that even if they are unable to boot the new image, they are able to restore the previous version and use the old one to ensure that your car is always functioning.
But where are you writing the old image if you're not carrying a double copy?
They are not using double copy, they are using the OS tree.
I understand, but where is physically stored?
On a single partition.
So you have another
OS tree
partition.
is something like JIT for whole file system.
I understand. Right. So you're downloading something.
Yes, you download it, then you apply reboot to the init ramfs. You, let's say, check out the new version.
So you need networking capabilities on your RAM disk.
No. You just do the checkout. Git checkout.
On local Git?
It's not JIT, it's OS tree, but it's a little bit equivalent.
I understand, but it's local. How can I check out if I cannot check out means from a remote source or from a local source?
Okay, so you are running your system. You download the upgrade. And put this on the disk.
Binary, right? It's a binary.
Binary.
Okay.
Then you reboot the system and hold on in init ramfs.
Okay.
And do that. You check out. You write the new version.
Okay. You write it. Okay. Perfect.
And then you try to boot it.
And it doesn't.
If it doesn't, then you reboot once again to init ramfs. Check out the old version and boot the old version.
But I have to keep a copy of the old one, right? Binary.
It's like JIT,
right?
So you may check out.
Perfect. When you say JIT, right, is locally.
Yes.
Okay, so this is a local, right?
Yeah.
Okay, so you're checking out locally. Okay, it's a little bit like a work because you don't have so many tools on the RAM disk, right, to handle these kind of checkouts operations.
Just a single tool.
That is like this OS 3, right?
Yeah.
Just the OS 3, and he can handle binaries.
Probably.
Because like Git actually complains about binaries sometimes, so there was it handles binaries.
Well,
right?
yeah.
Okay.
It's for the whole file system, so.
I don't want to carry the entire file system file by file, right? If I'm using WIC or other really compressed image types, I don't want to deal with all the file system file by file. That's kind of over, it's a lot. But anyway, I understand what you're saying. Just my point of view is very unlikely. So someone should make sure that the update is actually working. But someone can upload the wrong one. So I know that you can be always in that situation. It happens. Yeah, totally true. But again, you cannot go anywhere from that part. So if that happens, the device is stuck.
As I understood, OS 3 is like a step when you...
You were talking about OS 3, right? So
yeah,
okay.
Yeah, you have your setup installed, and then you install a whole package, and then you did a commit. So it's not one file committed, it's the whole
file system.
Mm-hmm. And this commit is atomic. So if it breaks, you will start your file system with the previous commit working, and if you succeed, the next one, but you can come back and.
Actually, it's like a double copy.
It's like a double copy.
If you have to update everything, you may need a partition that is twice the size of what you need, because maybe you have an update that should update everything. So your Git will have to contain both.
Not really, because there is a compression.
Well, you rely on your Git thing.
Yeah, but you still need another partition.
But it's a double.
No, it's on the same partition. It's just the directory structure. Like in Git, you have the .git directory where you hold only the objects.
And it would be like in the recovery run disk. All these things live in the recovery run disk?
No, it's living in the root partition.
Yeah, but I'm overwriting the root partition.
No, you're not overwriting the root partition, you are overwriting single objects.
Oh, so okay, so I'm not I'm not using anymore a raw writing.
Yes.
Okay, so what you're saying that I'm changing the way I'm writing the root.
Exactly.
Okay, I understand. Okay. I didn't get that part. Because here, what we are doing most of the time is using this. So we have raw images, and we just write raw images, right? In your case, no, it's not raw images.
It's not raw image. It may
okay.
Archive or anything.
So this
like
is actually
this.
something that we should talk with Stefano, because the device structure. So the device, the data type images, right, supports two or three types. So it would be interesting to understand which type should be to handle that type of file. So yeah, okay, I understand. So it's another type of write. Okay.
Yeah. So instead of doing DD to the disk, you just simply unpack the archive or do.
Gotcha. So let me ask you a thing. So today Android, it can be like faulty, right? If your manufacturer releases like a bad thing, your phone is done. Right?
Not really. You have to do the manual recovery from the SD card or
no.
connect this via USB.
You have your phone, right? Now with the single image procedure that Android features, if I'm releasing you a bad image, you flash a bad image.
Yes, and then you can connect your phone via USB to the computer and serve the right image using ADB or put this on the micro SD card.
I'm not sure that you run.
That's after the fact. Yeah, phone is not going to be booted.
The phone is not to be booted, right? So you're using an external tools to save the situation.
Yeah. Exactly. So it's exactly the same as you present. I totally agree with you.
So it's like, I understand, but so we can make more reliable actually to have a backup situation even in a single partition mode.
Yeah.
Okay, that makes sense.
Just another. Could you re-explain the relationship with the bootloader? To which extent you rely on features from the bootloader with your setup?
So the question is if I'm relying on a special bootloader version?
Or at least, what do you expect from the bootloader to comply with this?
So we're using the mainline bootloader right now. So nothing is...
Mainline means U-boot.
U-boot, yeah, U-boot. Oh, you mean which bootloader?
You must use U-boot.
U-boot, yes, U-boot. I'm using U-boot right now.
What does U-boot exactly needs to do to cover this? From what I thought was just to understand that it should.
Yeah, nothing. Because the only things we really need is to change an environment variable.
To change an environment variable inside the U-boots.
Yeah. So from here, I can use the firmware utilities and do firmware setemp uState equal 1. So I'm writing that value in U-boot.
So if you'd like to replace the bootloader, your bootloader has to provide an option to change the environment variable or.
Well, it was
like
not
this.
to know exactly if you really need U-boot or any other skill. Is that with this setup you must write something into a boot image, which itself is expected to be authenticated.
No, because U-boot. Okay, so I'm writing on U-boot, right? U-boot is like in a space that is out of this context, so it's not updated at all. What I'm doing from the user space is just write this variable value.
In the U-boot environment?
Yes. No partition. I'm writing on U-boot. The firmware utilities, they handle everything for me. So when I do, like, literally, there was a slide of firmware set m uState equal 1, I'm writing here, not in the partition where I'm not updating this partition. This is not a partition like space, it's just like a raw.
This environment cannot be signed. Simple. You cannot.
Environment cannot be
the
signed.
environment variable cannot be on a signed partition. It cannot be inside U-boot. It has to be on a separate partition which is not signed and not verified during the boot.
So it can be corrupted by something else, and you can externally ask your bootloader to do something else, and then you lose your
That's why you
verified
should
boot
put only
feature.
this variable on a separate partition and pull all other variables into on partition which is signed and verified.
Yeah, you must find a means so that this information is somewhere that does not need
It
an
has to
authentication.
be somewhere else. It cannot be on a signed partition because you are modifying this.
Yeah, I guess Android uses some raw partitions to carry such information between the boot stage or the recovery stage.
I don't know.
Well, I don't know neither.
Well, we can continue outside, because they are kick us out.
Sorry.
Yeah, if you look,
Thank you very much.